All right, so what we're looking at here is this top. Sorry, my phone was ringing. We're going to look here as the first item on our weekly agenda. We want to describe the relationship between theoretical resonant frequencies and formant frequencies. So, Fant, who you'll hear about quite a lot in our textbook and through the course of this class. We've talked about him already, but you'll probably hear the name a few times. So this guy, Fant, calculated theoretical resonant frequencies using the area function for a given vowel. And the way that he did that was based on the combination of small tubes. You can see here, we've seen this a few times, but there's a whole bunch of different small tubes. It's easy to figure out the area of a tube of a constant size. Or, well, yeah, the area of a tube of a constant configuration, I should say. So figuring out the whole vocal tract is really difficult because it's not a constant configuration. So we break it into a bunch of different small tubes of constant configurations. Of course, more tubes, you have a better representation of what's going on in the vocal tract. Fewer tubes, you're losing some. But the thing is, we're never quite achieving 100% explanatory power, right? And so this is kind of like, imagine you take the coastline of England, which is an island, the top of Europe. And so what you can do is you're going to measure it. You're going to measure the coastline of England. And the first thing I give you is a yardstick. So you're going to walk out there with a yardstick. If you're one of my students who aren't in the United States, a meter stick. They're roughly the same thing. So you go out with your yardstick or meter stick, and you're going to measure the coastline of England. Well, you're going to have things like little areas where the coast comes in, like this. And you've got your yardstick, and it's going to kind of go over that. So your yardstick isn't taking that into account. So you get a measurement of the entire country with the yardstick. Then I give you a ruler, 1 foot ruler, or a third of a meter, roughly, I guess, people who aren't in the U.S. So you get a 1 foot ruler, and now you can actually do things like if you had, you could turn your ruler and measure part of this little nook and cranny that's on the edge of the English coastline. And then the next thing I give you is a really tiny, like just centimeters ruler. So you're going to use that. And then I'm going to give you an even tinier thing. And then I'm going to tell you, now measure it in the edge of a dime, right? So you're going to take a dime out and you're going to use the edge of a dime and you're going to count how many edges of dimes it is. You're going to get a different answer every time because you're kind of like zooming in more and more. Right, your pixels are getting finer and finer grained, but they're still pixels, and this is true for these measurements that you're taking too. Like your stick is getting shorter and shorter, so you can fit into different cavities and measure them with greater accuracy. But there's still always going to be some sort of straight edge. There's still going to be something that you can't measure. And we're talking like down to the atomic level. There's still stuff that you can't totally measure. So you could have like you can have a ruler that's like 5 atoms long, and you're still not going to be able to accurately measure the coastline of England because there's still going to be like little nooks and crannies in those atoms that you just can't measure. And this is true for the vocal tract as well. So you can see that we have all these different tubes, but you can see that there are like gradations. There's like a staircaseness to these tubes. And of course, that's not what it's like in here. Even if our mouths were completely flat, it wouldn't have the staircase kind of look to it. But then we've also got ridges in there. We've got taste buds and other bumps on our tongue. So there's all sorts of imperfections that are going to change very slightly, but it's going to change the theoretical resonant frequencies and the actual measured resonant frequencies. Well, that doesn't mean the theoretical resonant frequencies don't matter. They're largely true. They make most sense. They're kind of like, this is our ideal resonant frequency, and then based on just individual differences, people's actual resonant frequencies are going to be around that. Still, really amazing to calculate all these theoretical resonant frequencies, and then they come out to be pretty close to most people's actual produced resonant frequencies. And then we've seen this guy over here, pretty often, and he's like kind of creepy looking in a way. So I thought maybe make him look a little less creepy. We can even add hair. But like, you're never going to be able to get away from the fact that he's a robot, because he's got this like strange vocal tract here that protrudes from the back of his head for some reason. Anyway, there's some nightmare fuel for you. Okay. So again, this is what I was talking about before. The theoretical spectrum versus the actual output spectrum. So theoretical is estimated, right? Output is what's actually measured, what actually emanates from the mouth. And of course, they're not the same. We wouldn't expect them to be the same. Think of how many times you've had maybe someone come to your house to do some work. They give you a cost estimate, but if it turns out that it took more time, they're not going to charge you the estimate. They're going to charge you a little more. Maybe sometimes they charge you a little less. That's never happened. But anyway, miles per gallon. You buy a car with estimated miles per gallon. And depending on your driving habits, you either get way less than that or you get way more than that. Totally, it's up to you. You're not making the average. The car maker is just kind of guessing what the average driver does, and they put the average mile per gallon on there, and maybe no one in the world actually gets exactly that average mile per gallon, because there's all individual differences. It's true for everything. Anything we estimate is just like, well, it's generally here, but not expected to be perfect. And we're going to see that come up. Okay, so what we can look at here, this is the theoretical. We've got these tubes, and we're like, this is how tubes should work. We can use perturbation theory to say that there's a notch here, a perturbation here, and that's going to change these frequencies slightly in different ways, and so we would expect something sort of like this to come out of our theoretical vowel. And so then we have somebody say the theoretical vowel. This is like a whole speech passage. We pull the vowel out of here and we measure it, and what we get is something much messier than what we see up here. And that's true. That's what we would expect. But if you look overall, you've got this peak, and then you've got this peak, and then you have this peak here. This is kind of an interesting accident here, this one at 567. So you go up again here, and then here. So you do kind of have this undulating pattern to it like you do up here, but it's not exactly the same because this is real data, right? And so it kind of depends on what's going on with the laryngeal buzz. Is it always uniform? No. The actual shape of the vocal tract isn't exactly what we predicted, but it's close. It's close enough. We can say, well, looking at this person's second format is a little higher than theoretical, but it's probably an E phoneme based on what we would expect from a typical E phoneme. All right. So theoretical resonant frequencies are all based on the model, and actual format frequencies are pulled from the spectral envelope. So the actual format frequencies would be like right here, and right here, and probably right here. So theoretical, we just compute the resonant frequency, and then actual format frequency we can just pull from our spectrum. It's going to be the peak that we see. All right. So this is mostly just kind of talking about the spectral envelope, finding those peaks again. So the vocal tract is going to shape the laryngeal buzz, like we talked about, right? It's going to shape the input signal. The spectral envelope is based on the speech output. basically what you do is you draw kind of a general curve connecting the peaks of the measured output frequencies. So you can see that in these two here. This curve just kind of connects these, and it's kind of a lazy curve that, you know, generally kind of gets close to these peaks. Some are below, some are above. It's kind of like if you remember from statistics, when you do a best fit line for a correlation, some points are above, some are below. You're just trying to come up with the best fit. And so that's what the spectral envelope does. It comes up with like the best fit curve for this actual spectral output. Here's another one. You can see this is the envelope here. These are all the different harmonic partials, and we want to kind of connect the peaks of our harmonic partials. Doing this, the spectral envelope will then mirror the theoretical resonant frequency, right? So we can draw this. This one on the top is even better. But you can see that this kind of looks like what we draw for vocal resonances. Cool. We use something called linear predictive coding to find the spectral envelope. You're not going to have to do that, but basically think of it like exactly what I explained before when you have like a linear trend for a correlation. If you think back to statistics, the points are going to basically go up like this. You have some dots that are above and below, but the general trend is like this. And we use that same basic idea, linear predictive coding, to kind of draw a bunch of trend lines, and that's how we make our spectral envelope. All right, so the harmonics and the formants are not necessarily aligned, though, when we do this. And so you can see in the top here, this, of course, is the resonant frequency. This is the filter. This is our theoretical vocal track that we have here. And the peak of this resonance right here does correspond perfectly with this third harmonic. Cool. The peak of this resonance corresponds perfectly with whatever this partial is. But you could also imagine that if the fundamental frequency changed, but the construction of the vocal tract did not change, then they wouldn't be aligned anymore, right? So the fundamental frequency shifts over, but the vocal tract stays the same. So now you have this peak of resonance here. It does not correspond to an actual frequency. It's somewhere between the two. And same here, somewhere between the two. So instead of having one frequency that, you know, is all the way past or even slightly amplified, you have two that are kind of similar in how much they're amplified. And so we kind of have to, this is why we have to use LPC, linear predictive coding, to try to decide what does the filter actually look like based on the output that we actually get. If there is no energy at the exact center of the resonance peak, then we can't measure the exact center of the resonance peak. We have to infer it from the 2 points that we actually do have. And I can show you that here. So I pulled this from, I made this in Audacity. I was going to say Prot. This clearly is not Prot. It looks too good. So I made this in Audacity. This is a 100, 200, 300, 400, and 500 hertz tone. It's peaking a little bit. That's my error. You can see it's kind of peaking a little bit. But this is so 100 to 500 hertz. And I put this filter on it. And so you can see that it's about 50 hertz that this is going to pass. Or no, it's 100 hertz, sorry. So it's centered on 100 hertz and 500 hertz, and it's going to pass about 100 hertz centered on 100 and 500. You can see that it's pretty sharp, the tuning on these. But it is centered at 100 and 500. This is the resulting output that we get. So this is the input frequency. It passes through this, and this is the output. You can see that it's pretty robust, right? Like our amplitude is close to 1. Here it was beyond 1. So we've taken some of the frequency components out. Basically, we've taken out 200 300 and 400. And this is what we get. However, if I do this, if I shift it over by 50 hertz, so I've shifted the 100 hertz to the right by 50 hertz, and I've shifted the 500 hertz to the left by 50 hertz. Now it's centered on 150 and 450. This is what I get. I use the same basic sound, this one here, and this is a different output. Just because the filter is not aligned with the actual peak frequency. Different output. What you can see here, look at where this is, you can see that we do have the same fundamental frequency in both of these. We can still reconstruct the actual sound. So if you look at where this repeats, we still have a 100 hertz tone, basically. But it's very different. It's a lot quieter. The timbre is going to be a little different between the two also, because this one, you can see that it's really carrying just 100 hertz, which is our general slope, and then 500 hertz within it. The one over here, it's carrying 100 hertz, but then it looks a little bit more like this signal, this kind of like decreasing stair-step thing going on here. So there'd be a timbric difference in addition to a huge and very noticeable amplitude difference. But anyway, take-home point here is the big difference between these two is where the filter peaks were aligned with the actual frequency peaks. They're not in the exact middle, so we'd have to do a different process on the right to reconstruct the actual signal than we would on the left. Like, we can see the left pretty well and see the actual signal, but on the right we'd have to reconstruct it with LPC. Okay, I forgot what that little arrow was for. Okay, so format and frequencies for male voices are going to be more accurate than for female voices or children's voices. And when I say accurate, I mean our measurement of the filter is going to be more accurate. The reason for that is a lower fundamental frequency has more closely spaced partials or harmonics, however you want to say it, partials or harmonics. But you can see here, this is a 100 hertz tone. We're going to have 100 hertz, 200 hertz, 300 hertz, 400 hertz. There's a partial every 100 hertz. So a filter of this size, we have more data points in there. So we can figure out the filter with much more accuracy. Then you see a 200 hertz. This is more like a female voice. We have 200 hertz, then 400 hertz, then 600 hertz. So with a 100 hertz fundamental, we've got 6 frequencies before we hit 600 hertz. With a 200 hertz fundamental, we only have 3. And then down here with the 300 hertz fundamental, like a child's voice, we only have 2 before we get to 600. So we're losing a lot of information before we get to 600 hertz. And that just continues beyond 600 hertz as well. So you can see that here to reconstruct this filter would be much harder because we don't have as much information. So we might not be as accurate at reconstructing the filter. And then here's the child's voice. We'd be probably very bad at reconstructing this filter, even though it's all the same filter. All right. And then lastly, the bandwidth of the filter can change the perception of vowel sounds. Now, we can think about this also as the formant bandwidth. So what's going to happen is the categorization doesn't change. An E is still going to sound like an E. However, the quality gets muffled. So it'll go from E to E or some, I don't know. That was mostly a pitch change. It's hard for me to like modulate my bandwidth. Sorry. I'm not perfect. So, but it's going to be muffled, essentially. It's not as easy to hear, but it's still an E. If you can hear it, you'd still say, oh, that's an E, but there's a lot of noise. You also end up with more dampening in the time domain. There's less accentuated peaks. It's kind of flatter. And it's also less intelligible. That goes along with muffled. So what I'm going to show you here is, this is white noise that I've taken and put a filter on. So again, I've got a filter that's centered at 100 hertz and 500 hertz. But if you look at the little green curve on there, it's actually pretty darn wide, right? So I've got it focused on 100 hertz and 500 hertz, and the edges of my filter go out 100 hertz on each side. So it's a 200 hertz wide filter centered on 100 and 500. And then the actual curve is pretty large. And so we filter the white noise with that filter, and this is what we get. We get these peaks. They're kind of wide. We have all this noise down here. And this is what it sounds like. Oh, hang on. I'm adding audio output capture so you can actually hear what I'm doing. Okay, hopefully this works. So this is what this is filtered white noise. Well, that was loud. Sorry about that. Let's bring it down again. You want to hear it again? This is filtered white noise. Of course, white noise, you know, is like... And this is what it sounds like with this filter on it. Okay. And now I made this second filter. They're centered on the same place, 100 hertz and 500 hertz. But they only extend 50 hertz out each way. So it's a 100 hertz wide filter now. And I've also made the little green curve a little bit sharper as well. So you can see that the representation on the right-hand side, you can see that they're more sharply tuned, basically. You can also see that it's louder. So you can see that this peak here on the right, this 500 hertz peak, reaches negative 35 dB, and over here it's a little bit below negative 36. So we've actually increased the loudness just by sharpening the tuning. That's it. Okay, and this is what it sounds like. Again, this is white noise with a filter on it. You can actually hear a tone in that this time. I mean, you sort of could before, but this time it actually sounds like maybe that's just a sine wave. If you want to hear it again. Again, this is filtered white noise. And this is an analog of what happens in the vocal tract if you have a wide versus narrow format bandwidth. A wide bandwidth is going to sound less intelligible, like this. And a narrow bandwidth is going to sound more intelligible, like that. Okay, well, just to cover what we've done, we looked at theoretical spectrum versus output spectrum, and you can see the difference between those, right? One is a very educated guess, and the other is this is exactly what this comes out. We've looked at the effect of fundamental frequencies on format frequencies. In essence, lower fundamental frequencies will allow you to guess the spectral envelope better, or to reconstruct, I should say, not guess. Lower format frequencies allow you to reconstruct the spectral envelope better. And lastly, bandwidth change. Wider bandwidth is going to be less intelligible, more muffled. Narrower bandwidth is more intelligible, less muffled, very sharp and crisp. All right, that's the end of this submodule, and I'll see you in the next one.